Hi guys, so we're going to look at question 8 from the 2015 paper 1 exam. So we have an oil spill occurring offshore in an area of calm water with no currents. The oil is spilling at a rate of 4 by 10 to the 6 centimeters cubed per minute, and the oil floats on top of the water. So the first question, complete the table below to show the total volume of oil on the water after each of the first 6 minutes. Alright, well, very simple start. We know that there is 4 by 10 to the 6 centimeters cubed per minute. We can assume that there's 0 to start off. So after 1 minute, there will be 4 by 10 to the 6 centimeters cubed. After 2, there's 8. After 3, there is 12, 16, 20, 24. Very simple start. So right, let's just what is the first question telling us? So we have 4 by 10 to the 6, calm water with no current, so it's not it's not moving away. Okay, so let's say the rate of oil spilled is 4 by 10 to the 6 centimeters cubed per minute. Alright, now on to our next. Let's just move it up a bit. Don't need all that space. Alright, draw a graph to show the total volume of oil in the water over the first 6 minutes. Well, it's just linear. So, and it starts from 0, so we start from 0, and there's 24 after 6 minutes, so we just get this graph. So after 1 minute there is 4, after 2 minutes there is 8, and so on and so forth until we have 24 by 10 to the 6 centimeters cubed after 6 minutes. Alright, very simple start to the question. Alright. The oil forms a circular oil slick 1 millimeter thick. Okay, circular 1 millimeter thick. Write an equation for the volume of oil in the slick in centimeters cubed when the radius is r centimeters. Alright, well so we sort of have, it's a circular oil slick 1 millimeter thick. So it's kind of like a cylinder. And so if we look at the volume of a cylinder, so circular 1 millimeter thick, and the volume, the formula for the volume of a cylinder is simply pi r squared, the area, times the height, pi r squared h. Okay, well, we have h. We know that h is 1 millimeter, which is 1/10 of a centimeter, 0.1 centimeters. And remember, we're working in centimeters. And so the volume would just be pi r squared over 10. Pi r squared over 10 centimeters cubed. Okay. Okay, now on to the second part of B. We want to find the rate in centimeters per minute at which the radius of this oil slick is increasing when the radius is 50 meters. Alright, so we're looking for dr dt. the rate of change of the radius with respect to time. Okay, well, we have this formula for r, which has r in it. So v equals pi r squared over 10. Okay, so we have this formula. So and we have r on the right. So if we differentiate this formula, so if we take the derivative of both sides, then we'll get dv dt equals the derivative d dt of pi r squared over 10. Okay, so how do we differentiate pi r squared over 10 with respect to t? There is no t in there. Well, we know that we have the chain rule. The chain rule is dy dx is equal to dy du by du dx. Okay, so if we differentiate this thing with respect to r and then multiply that by dr dt, then we'll get, so we'll have, so d dt of this, of pi r squared over 10 is equal to, because that's our y, and then if we differentiate y with respect or this thing with respect to r, we'll get, so this is equal to d dr pi r squared over 10 multiplied by dr dt. And now we know how to differentiate this with respect to r. It's just 2 pi r over 10, bring down the power, and then multiply this by dr dt. Okay, so now we have dv dt equals 2 pi r over 10 by dr dt. Okay, and we're looking for dr dt. We are looking for dr dt. So we have this expression and we're looking for this. Well, we have r, we know what r is, and the other variable is dv dt. Do we know what dv dt is? Well, we actually do know what dv dt is. That comes at the start of the question. We know that the rate of oil spilled is 4 by 10 to the 6 per minute. So dv dt is just a constant equals 4 by 10 to the 6. Okay, and r is 50 meters, which is just the same as 50 by 100, 5,000 centimeters. Okay, so 4 by 10 to the 6 equals 2 pi 5,000 over 10 by dr dt. Okay, and now we have, if we divide the left-hand side by 2 pi, by 10,000 pi over 10, so just 4 by 10 to the 6 all over 1,000 pi, then we get about 1273.24. So 1273.24 equals dr dt. Okay, so our answer is 1273.24 centimeters per minute. Remember to get the right units. Okay. Now this is a little bit tricky, but it's just the important thing here is to remember the chain rule. When you're differentiating something with respect to a variable that's not there, always best to use the chain rule. Now on to part C. Show that the area of water covered by the oil slick, is increasing at a constant rate of 4 by 10 to the 7 centimeters squared per minute. Okay, so we know that it's expanding kind of in a circle, which is 1 millimeter thick. So, well, we don't have a formula for this area, so let's try and make one. Okay, so we know that the volume is equal to the area by the height. This is kind of the definition of a volume of a cylinder. Okay, so now we have the area in some expression, and we know that h is equal to 0.1. So V equals A over 10. So let's again take the derivative of both sides. So dV dt is equal to d dt of A over 10. So again, we're trying to take the derivative with respect to t of an expression that doesn't have t. So again, we're just going to use the chain rule. So we differentiate with respect to the variable that we have. So d dA of this thing, A over 10, and then multiply that by dA over dt. This is just the chain rule. And then we get, so if we differentiate, so this thing, so the derivative with respect to A of A over 10 is just 1 over 10, very simple. So we just get dV dt equals 1 over 10, and then we have dA dt, and we're looking for dA dt. This is what we're looking for. And we know dV dt is 4 by 10 to the 6. So if we just multiply both sides by 10, we get that dA dt is equal to 4 by 10 to the 7. And the units are centimeters squared per minute. And we've shown what they asked us to show. So dA dt is equal to 4 by 10 to the 7. Okay. Okay, now, final part. The nearest land is 1 kilometers from the point at which the oil spill began. Okay, find how long it will take for the oil slick to reach land. Answer correct to the nearest hour. Okay, answer correct to the nearest hour. Okay. Well, let's say the coastline looks something like this, and the oil slick starts, say, here. It's going to be something like this. Okay. And let's just make that a bit bigger. So this is the center. All right, so it's going to look something like this, okay? And it has a radius. Let's just, oops. Okay, so this radius is 1 kilometer. Okay. So what's the area at this? What's the area of this thing at this point? Well, the area is pi r squared, and it's 1 kilometer, so that's 1,000 meters, which is 100,000 centimeters. So the area is pi by 100,000 squared. And so that's 100,000 squared pi is 3.14 by 10 to the 10. 3.14 by 10 to the power of 10. Okay. So the area at this point is 3.14 by 10 to the 10. So now, a nice way of thinking about this is, how long will it take for the area to reach 3.14 by 10 to the 10 centimeters squared? All right, well, we know the area is increasing from 0 at a constant rate of 4 by 10 to the 7 centimeters per minute. All right, so if it starts at 0, and when it reaches land it's 3.414 by 10 to the 10, how long does it take to reach that? Well, we can actually just divide. So we get 3.14, because it's doing it linearly, by 10 to the 10 over 4 by 10 to the 7, and this will give us the amount of minutes it takes. So if we divide this by 4 by 10 to the 7, we get exactly 250 pi. We get 250 pi, which is just 785.4. 785.4. All right, and this is the amount of minutes it takes. And 785.4 minutes, well, let's just divide by 60, and we get 13.08. 13.08. And that'll just round to 13 hours. And that's the end of the question.